Hello class, welcome to lesson 6.1, which is all about graphing systems of equations. By the end of this lesson, you should be able to determine the number of solutions a system of linear equations has, and you should also be able to solve systems of linear equations by graphing. Okay, so a few things that you want to make sure you know as far as terminology goes, vocab. Consistent and independent, as well as consistent and dependent and inconsistent. Those are kind of our new words. We've seen no solution before. We haven't really used the term infinite before, but that just means like there's so many answers that we can't even count them all. It's kind of like the equivalent of all real numbers, okay? Or exactly one. So let's go through what do some of these things mean. So when we're talking about systems of equations, we're talking about when you have more than one line that is graphed, okay? So if you look at the very first example that they give you, you have two lines that are intersecting at exactly one point there, okay? So there's one solution because the two lines only cross once, okay? Whenever you have two lines that cross in just one place, you call that graph consistent and independent. Consistent means that it intersects at one point. So consistent means that it's at exactly one point. Independent means that they are not parallel. Okay? Independent means that they are not parallel. If we look at our middle example, we have consistent and dependent with an infinite number of solutions. What this means is where you see that blue line on that graph, that means that there's more than one equation that will give you that same line. So that means if I give you two equations and they happen to end up being the same exact line, that is known as consistent and dependent, and there are infinite many solutions. So two equations or more and one line, okay? And then if you look at our last option, you have two lines that are parallel. They are never going to meet, so that means there's no solution because our solution is always where the lines intersect. So parallel lines never intersect. That means they are no solution. And we describe that graph as being inconsistent, okay? Excuse me. So let's look. Example 1, use the graph to determine whether each system is consistent or inconsistent. Okay, so do they intersect? Do they not intersect? And if it is independent or dependent. Is it two separate lines or is it the same line? Okay, that's basically what that question is asking. So let's look at letter A up here. We have y equals negative x plus 1. If I look, that's this line right here. It highlights it for me. And y equals negative x plus 4. So if I look, I see these lines look parallel. If I double check, my slope is negative 1, negative 1. And whenever you have slopes that are the same, you know that they are parallel. So what did we learn from the last slide? When you have parallel lines, it is called inconsistent. Okay, so we are just going to say inconsistent. When you have an inconsistent graph or two parallel lines, you don't have to say whether it's independent or dependent. Okay, you just say it's inconsistent. And then let's look at our next one. We have the y equals x minus 3 line, and we have the y equals negative x plus 1. So we have that purple and orange line. They intersect at this one point. So they intersect at one point. That means it's consistent. And it is it the same line or is it two separate lines? Two separate lines, so it's known as independent. So consistent and independent. Alright. Go ahead and try to figure this one out on your own, see how you do. Hopefully you determined that this first example is consistent and independent, but go ahead and try another one just in case. And hopefully you decided that this second graph is inconsistent. If you have any questions about those, please be sure to ask. Let's look at example 2. Now we're going to graph each system and determine the number of solutions that it has. If it has one solution, you name it. Okay? So let's start by graphing our first line. We have y equals 2x plus 3. So remember, this is in slope-intercept form. This is my y-intercept, so where it crosses the y-axis. And this is my slope, so my rise over my run. So I start with my y-intercept, it's positive 3. My slope is a positive 2, so I rise 2, I run 1, rise 2, run 1, or I can fall 2, go back 1. I'm just going to do several of these to help improve my line. Okay? And then the next thing that I can do is I can either graph this next one just like it is, or I can solve it for y and graph it like I graphed the first one. I'm going to graph it by, I don't know if you guys remember, where we would cover up one of the variables. So we can figure out if we make y 0, we have 8x equals negative 12, or x equals negative 12 eighths, which is negative. 2 goes into both of those, and so does 4. So if I take a 4 out, I have 3 halves. So x crosses at negative 3 halves. And then if I have my y, I can do negative 4y equals negative 12, or y equals 3. So based on my line, like, it's really hard to tell because of the way I draw my lines, and it's hard to freehand lines. But these are actually the same. This is the same line. One way you could tell is if we did solve this for y, we have 8x minus 4y equals negative 12. Negative 4y equals negative 8x minus 12. Y equals 2x plus 3. So you can see if I would have solved it for y, I would see I have the same exact problem, okay? So that means that this graph has infinitely many solutions, okay? Let's look at the second part B, the second example here. We have x minus 2y equals 4. I can solve for y if I wanted, say negative 2y equals negative x, plus 4. And I could say y equals positive 1/2 x minus 2. If I do that, I go down to 2. I go up 1 over 2. So that's one way that I can graph, or I could graph using the intercepts, which I'll do with the next one. Or if I do it the other way, I can say x equals negative 2, or negative 2y equals negative 2. So y equals 1. So if I graph those two, x equals negative 2 here, y equals 1 here. It's a little harder to keep going, but I can see my slope is 1. If I look at this graph, or you can see this is 2, negative 2 over negative 2, or positive 2 over 2. So then if I connect all of these points, and I go, you can see I intersected at one point right there. And so that means my solution would be at negative 8. And then this is negative 8, negative 6. So that would be my solution. I would write on my paper -8, -6, and I would show the graph, okay? Because today we are practicing graphing. I'll show you a different way another day. Go ahead in your notes, graph this system of equations and determine whether the system has no solution, one solution, or infinitely many solutions. If it has one solution, name it. Hopefully you said that there was one solution and it's at 0, 3. All right, let's look at example 3. If we graph this system of equations and we want to determine the number of solutions it has, and then if it has one solution, name it. I saved a little bit of time because I'm going to trust that you guys can get back in the swing of things with graphing. If you need help with that or reminder, let me know. So let's look at this graph. I have these two lines graphed here. So I've done the first part, graph each system, determine the number of solutions. I see it intersects at one point, so that means there's one solution, and that solution is the coordinate that they intersect. So if I look, I go 1, 2, 3, so my x value is 3. I go up 1, so my solution is 3, 1. All right, so I have a little kind of shortcut thing here to help you. When both equations are in the form y equals mx plus b, our slope-intercept, here are a few tricks that you can use based on the values of m and b. Okay, so if you have two different m values, or 3 or 4, however many graphs you're doing, if they are all different values, you're going to have one solution. If you have the same m value, or the same slope, but different b values, that means you have two parallel lines. It means you have two lines that look like this, and that means no solution. If you have the same slope and the same b value, that means you have the same equation, and the same equation means that it has infinitely many solutions, okay? So that's one benefit of rewriting your equations in the y equals mx plus b form, okay? So let's look at example 4. We have Naresh rode 20 miles last week and plans to ride 35 miles per week. Diego rode 50 miles last week and plans to ride 25 miles per week. Predict the week in which Naresh and Diego will have ridden the same number of miles. Okay, so if I think about this, Naresh rode 20 miles last week. So I'm going to say n equals, and then 20 miles last week and 35 miles per week, plus the 20 he rode last week. Diego rode 50 miles last week, plus plans to ride 25 miles per week. So that would be how I set up my equation, and then I would just have to go and graph it. So if I were to graph it, it should look something, if I could get that to go away, should be able to close. There we go. So if I graph it, it's going to look something like this, where I have the two graphs going, and if I look really carefully, I can see that they intersect at this point right here, okay? So what is that point? If we look, it's 3 weeks. Time is always our x value, right? And then if I look, it's approximately 125. It's about a halfway between. So by graphing, I can see that after 3 weeks, they will have both ridden about 125 miles. One thing that you can do to check, is my graph correct? Am I just guessing? Plug those numbers in. So if we do 35 times 3 plus 20, 35 plus times 3 plus 20, that is 125. Okay, so that one works. And if I do 25 times 3 plus 50, 75 plus 50 is also 125. So, that is where they're going to meet. After 3 weeks, they both have ridden 125 miles exactly. Okay? So you have one example to go ahead and try and see if you can figure it out. Go ahead. Hopefully you were able to determine that Alex and Amber will have the same amount of money in 5 weeks. If you have any questions on how to set that up or any questions about 6-1 in general, please be sure to come see me. I'd be more than happy to help you. Have a fantastic day.